Hello 8th class students. Now we are about to finish the sound chapter. The video which I am going to give you is going to cover the entire sound chapter. Already we have seen this video in the digital format in our previous weeks. But this video is very important as it covers all the activities with very good visual explanations so that you can grasp those concepts very clearly. Okay, thank you.
Introduction. The first day, a teacher enters into your classroom. What do you say to the teacher? You all wish a very good morning to the teacher. Suppose, if all the doors in your room are closed, then how can you guess whether anyone is crossing the room? Yes, you can identify it by hearing the footsteps of the person. Objectives. At the end of this lesson, you'll be able to understand that sound is caused by vibrations, know about the musical instruments, identify the sound from musical instruments, understand how sound is produced and propagated by humans, acquire knowledge where the sound requires a medium for propagation, understand the propagation of sound in liquids and solids, analyze the working of human ear, define amplitude, time period and frequency of a vibration, distinguish between loudness and pitch, analyze the audible and inaudible sounds, differentiate between noise and music, understand about the noise pollution and its control measure. Sound is produced by a vibrating body. Sound is a pressure distribution that moves through a medium in the form of mechanical waves. When a force is exerted on an atom, it moves from its rest or equilibrium position and exerts a force on the adjacent particles. These adjacent particles are moved from their rest position, and this continues throughout the medium. This transfer of energy from one particle to the next is how sound travels through a medium. The words mechanical wave is used to describe the distribution of energy through a medium by the transfer of energy from one particle to the next. Sound waves that travel parallel to the direction of the particle movement are called longitudinal waves. However, it is possible to produce other types. Waves which move perpendicular to the direction of particle movement are called transverse waves. After the train crosses the station, if you keep your ear on the rail track, you can clearly hear the vibrations in the rail track. This confirms that sound travels through solids. How is sound produced by human beings? Voice box in human. Sound is produced by the voice box or the larynx in humans. The part which moves when you swallow is known as voice box, which is at the upper end of the windpipe. Two vocal cords are stretched across the voice box. When lungs force air, vocal cords vibrate, producing sound. When the vocal cords are tight and thin, the type or quality of voice is different from that when they are loose and thick. Sound requires a medium for propagation. Place an electric bell in an air-filled jar. You can hear the sound of the electric bell which is ringing. Now suck out the air from the jar using the vacuum pump. As you suck the air out, the sound starts fainting. As all the air sucked out, the sound fully faints. This experiment confirms that a medium is required for the propagation of sound. Sound travels through solids. Ask your friend to hit the bench using a stick at one corner. Keep your ear on the bench at the other corner. As your friend hit the bench, you can hear the sound at the other corner. This confirms that sound travels through solids. Sound travels through air, gases. What you hear is the propagation of sound through air. If there is no air, we can't hear the sound inside the room. We all hear the sound of moving flight. It is due to the propagation of sound through air, gases, which reaches our ear. Sound travels through water, liquids. Place the bell in a beaker filled with water and make it sound. You can hear the sound, which confirms that sound can travel through liquids. Communication between dolphins also confirms that sound travels through liquids as well. We hear sound through our ears. The shape of the outer part of the ear is like a funnel. Sound enters and travels down a canal at the end of which a thin membrane is stretched tightly called eardrum. Sound vibrations make the eardrum vibrate, and the eardrum sends vibrations to the inner ear, and through inner ear it goes to the brain. This is how we hear sound. Amplitude, time period, frequency. Amplitude. Amplitude of the sound is nothing but the loudness or the amount of maximum displacement of the particles while the sound is produced. When the amplitude of the vibration is large, the sound produced is loud. When the amplitude is small, the sound is feeble. Frequency of sound. The number of oscillations per second is called the frequency of the oscillation. Frequency is expressed in terms of hertz. Loudness and pitch. Loudness depends on the amplitude of vibrations. Loudness of sound is proportional to the square of the amplitude of the vibration producing the sound. If the amplitude becomes twice, the loudness increases by a factor of 4. The loudness is expressed in a unit called decibel, dB. The following table gives some idea of the loudness of sound coming from various sources. Above 80 dB, the noise becomes physically painful. Pitch. The two sounds are equally loud. They differ in some way. The difference in sound is due to the shrillness or pitch of the sound. If the sound has high frequency, then it has high pitch or shrillness. If the frequency of vibration is low, then it has low pitch, that is, vibration of drums. Audible sounds. Sounds which we can hear is about 20 Hz to 20,000 Hz. These sounds are called audible sounds. Ultrasonic sounds. These squirrels communicate with each other with a frequency greater than 20,000 Hz. These sounds are called ultrasonic. Dogs, whales have the ability to hear ultrasonic sounds. The ultrasonics are used to take the scan pictures of various vital organs. Infrasonic sounds. Sounds which have frequency less than 20 Hz are termed as infrasonics. Music and noise. Sounds which are pleasant to hear are called as music. Here we have number of instruments which produces pleasing sound. Noise. Sounds which gives discomfort to hear. Such unpleasant sounds are called as noise. For example, when a cup of glass breaks, it produces noise. Noise pollution and its control. Presence of excessive or unwanted sounds in the environment is called noise pollution. The major cause for noise pollution is sounds of vehicles, explosions including bursting of crackers, machines, loudspeakers, etc. Television and transistor radio at high volumes, some kitchen appliances, desert coolers, air conditioners all contribute to noise pollution. Summary. Let us summarize what we have learned. Sound is produced by vibrating objects and it is carried in all directions in a medium. The to and fro or back and forth motion of an object is termed as vibration. In humans, the sound is produced by the voice box or the larynx. Sound needs a medium to travel. The sound cannot travel through vacuum. We hear sound through our ears. Position is called the amplitude of vibration. The to and fro motion of an object is called oscillation motion. The number of oscillations or vibrations per second is called the frequency of oscillation. The frequency of a body is expressed in hertz. Larger the amplitude of vibration, louder is the sound. Higher the frequency of vibration, the higher is the pitch or shrill is the sound. For human ears, the range of audible frequencies is roughly from 20 to 20,000 Hz. The presence of excessive or unwanted sound in the atmosphere is called noise pollution. Major causes of noise pollution are sounds of vehicles, explosions including bursting of crackers, machines, loudspeakers, etc. Plantation on the roadside and elsewhere can reduce the noise pollution.
From our past videos, we know that light follows law of reflection after being incident on a surface. Just like the light waves, sound waves also get reflected from the surface of a solid. They also follow the same law of reflection. Let us see what that law is. Say we have our source which is emitting sound, and assume one of the sound waves strikes the surface at this point. Let's draw a normal to this surface. Normal is nothing but the line which is perpendicular to the surface at the point of incidence. Now this wave will be reflected from the surface. The law of reflection tells us that this sound wave will be reflected back in such a way that the angle of incidence I is equal to the angle of reflection R. Also, the incident ray, the reflected ray, and the normal will all lie in the same plane. What if a wave is incident perpendicular to the surface? Well, in that case, the reflected sound will travel back in the opposite direction along the same line. Here is one demonstration that you can perform at home to verify these laws. Take two small hollow cylindrical shaped objects which are open from both ends. Two straight hollow pipes would suffice. Place them on the table like this near the wall. We also need to make sure that the table is covered with a white cardboard paper before keeping the pipes on it. Place a running clock near the open end of the pipe facing you. And now keep your ear near the open end of the other pipe. Did you hear the sound of the ticks coming from the pipe? Adjust the pipes a little until the sound is clearer. At one point, it will be very clear. This is an example of reflection of sound. Yes, you are hearing the reflected sound. The sound wave from the clock passes through this pipe and is incident on the wall. It gets reflected and passes through the other pipe and enters your ear. You will notice that these two angles are approximately equal. The angle of incidence will be equal to the angle of reflection if we ignore any human errors. Echo is another example where one is able to hear the reflected sound. What is an echo? The repetition of the same sound again and again is what we call an echo. Where do we hear an echo? Well, we usually hear it in empty spaces bounded by at least one tall surface. For example, when we're inside a large canyon or when we're shouting in a deep empty well from above. If we clap in an open space standing against a tall wall, we will also hear the sound of our clap again and again. Why does it happen? The sound from a clap travels in all the possible directions. When it collides with the obstacle, it gets reflected back. These reflected sound waves then travel towards us and we hear faint repetitions of our clap again and again. But hold on, are there any conditions? Or will we hear an echo in any and every case? Yes, there are a few conditions. The echo depends on the temperature of the surroundings and the distance between you and the point of reflection. Let me give you an example. Assume that the temperature of the surroundings is approximately 22 degrees Celsius. At this temperature, the distance between you and the wall has to be at least 17.2 meters for you to hear an echo. Only if it's equal to or greater than 17.2 meters, you may hear an echo. Otherwise, you wouldn't. But why did we have this condition? What if the temperature is different? What if the distance is less than 17.2 meters? Are there any other conditions apart from temperature and distance? We will answer these questions in our next video. We have seen how sound propagates through a medium. When the object vibrates, It creates the disturbance in the surrounding medium, and this disturbance is what we call a sound wave. The wave travels in the medium in the form of compressions and rarefactions. But in which direction do the particles of the medium vibrate? Before we answer that question, we will talk about longitudinal waves. What are longitudinal waves? Let me tell you the fancy definition first. Waves in which the particles of a medium vibrate in a direction parallel or anti-parallel to the direction of energy transport are called longitudinal waves. What does that mean? Before we get to the statement, do you remember what parallel and anti-parallel mean? Parallel would be two vectors like this, and anti-parallel will be two vectors like this. Parallel but in opposite direction. Now coming back to the statement, it means that if the wave travels in this direction, then the particles of the medium also move to and fro along this direction only. So the displacement of particles is parallel or anti-parallel to the direction of the propagation of wave. Is sound wave a longitudinal wave? Take this example and try to find out. Yes, sound waves are indeed longitudinal waves. We see this in this example that the particles of the medium are vibrating in the direction of propagation of wave. Sound waves are also called pressure waves. Can you tell me why? It is because the sound wave consists of the repeating pattern of high pressure regions called compressions and low pressure regions called rarefactions through the medium. But wait, hold on. Are there waves in which the displacement of particles of the medium is not in the direction of propagation of the wave? The answer is yes. Let's see one example in which the propagation of the particles is perpendicular to the direction of propagation of the wave. Take a string with one end fixed to the wall. This end is fixed at the wall here, and this one is in your hand. We see a wave when we give the string an upward jerk from this end. What do you notice here? In what direction are the particles of the string moving? Up and down, right? And what about the direction of the propagation of the wave? It's moving to the right. Let me repeat it once. The particles in the string are moving up and down while the direction of propagation of the wave is towards the right. The particles are vibrating in a direction perpendicular to the direction of the wave. Such waves are called transverse waves. So are sound waves transverse waves? The answer is no, and it's because the particles of the medium are vibrating in the direction of propagation of wave. Here is a quick recap of what we did today. We saw that longitudinal waves are the waves in which particles of the medium vibrate in a direction parallel to the direction of motion. Sound waves are longitudinal waves. Sound propagates through the medium in the form of high pressure and low pressure regions. Hence, sound waves are also called pressure waves. And at the end, we saw what transverse waves mean. They are waves in which particles vibrate at right angles to the direction of its propagation. In the next video, we will understand more about the propagation of sound waves. See you there. In videos, we have learnt that sound needs a medium to travel. The medium can be a solid, liquid or gas. For example, a doctor uses a stethoscope to hear the sound of our heartbeat. Here the medium of propagation is a solid. Can you think of any example where the medium is a liquid? When you place your ears close to the surface of water, you will still be able to hear the sound from bodies or objects inside. Yes, this is an example where the medium is a liquid. And air is the most common medium through which the sound travels. And air, as we know, is gaseous. What is a vacuum? Vacuum is a space void of any matter. It means that it's a space that does not have any matter. For us humans, it's practically impossible to find or create 100% vacuum. But is there any place which comes close to a vacuum? Yes, the outer space is the closest approximation to a perfect vacuum. This is the reason why we are unable to hear any explosions from stars or planets here on Earth. As outer space is almost a vacuum, the sound from these explosions cannot travel to us. Let us see one experiment. Here we have an electric bell jar. A bell jar is a glass jar whose shape is similar to that of a bell. So we have a glass jar in which electric bell is fixed with the help of a cork. We call it an electric bell because it requires electrical energy to work. This bell is connected to an external battery and key. The glass jar also has a vacuum pump attached at the bottom. When we close the key, the current starts to flow and the hammer starts to strike the gong and continues to do so. We hear the sound clearly. Now we start pumping the air out of the glass jar through the vacuum pump. Is the sound getting louder or is it getting fainter? Yes, the sound is getting fainter. We see that as the amount of air is reducing in the jar, the intensity of sound is decreasing. Although we can see the hammer striking the gong, the sound we hear is very feeble. This is because we create a vacuum inside of the glass jar when we remove the air out. Note that earlier we said that we cannot create 100% vacuum. Hence we cannot remove all the air from the glass jar. So there will be some soft sound that we will be able to hear. We can also perform the same experiment using an alarm clock. Instead of the electric bell, we place ringing alarm clock inside the glass jar. We don't need battery and key in this case. Initially, we will hear the sound of an alarm. But when we try to pump the air out of the jar, the intensity of sound will get lower and the sound will get fainter. Note here that the alarm clock should be chosen in such a way that it can easily pass through the opening of the glass jar. Let us do one more experiment which you can perform at home. Take an empty glass and a cell phone. Keep this cell phone in an empty glass. Ask someone to give you a ring on this phone. What do you notice? Yes, you will hear the sound loud and clear. Now if you put your hands around the open face of the glass like this and try to suck the air from the glass, do you hear the same intensity of sound? Is the sound getting fainter now? Yes, we see as we suck the air out of the glass, the sound gets fainter. And why is that? It's because a new vacuum is created in the glass when we suck the air out from it.
कुछ साउंड सुनने में बहुत सुखद होते हैं। एग्जाम्पल के तौर पर म्यूजिकल इंस्ट्रूमेंट्स जैसे कि फ्लूट, हारमोनियम, वायलिन इत्यादि की साउंड। हमारे जीवन में ऐसी कौन सी साउंड्स हैं जिन्हें हम पसंद नहीं करते हैं? सड़क पर चलने वाले वाहनों की आवाज, पटाखों की आवाज, जुलूसों के दौरान लाउड स्पीकर से आने वाली आवाज इत्यादि कुछ ऐसी साउंड्स हैं जिन्हें हम पसंद नहीं करते हैं। कभी कभी अगर म्यूजिकल इंस्ट्रूमेंट्स जोर से बजाए जाएं तो सिर में दर्द कर देते हैं। ऐसी अप्रिय और अवांछित साउंड्स को नॉइज कहा जाता है। हम सब जानते हैं कि एयर पोल्यूशन क्या है ना? हवा में अनचाही गैसेस और पार्टिकल्स एयर पोल्यूशन के लिए जिम्मेदार होती हैं। उसी तरह जरूरत से ज्यादा और अनचाही साउंड्स का होना नॉइज पोल्यूशन के लिए जिम्मेदार होता है। जी हाँ, कुछ साउंड्स नॉइज पोल्यूशन का कारण होते हैं और एयर पोल्यूशन की तरह ही इसके भी मानव शरीर पर हानिकारक प्रभाव होते हैं। चलिए मनुष्य पर नॉइज पोल्यूशन के कुछ हानिकारक प्रभाव देखते हैं। पहले होगा नींद की कमी। खास करके रात के समय में आसपास से आने वाली तेज साउंड हमें अच्छे से सोने नहीं देती हैं और अगर हमें अच्छा आराम नहीं मिलता है तो हम अपना कंसंट्रेशन खो देते हैं और हर समय चिड़चिड़े या परेशान रहते हैं, जिससे कुछ भी अच्छा नहीं होता है। अगला होगा हाई ब्लड प्रेशर या हाइपरटेंशन। तेज साउंड्स हमारे दिल की धड़कन को बढ़ा देती हैं, जो बदले में हमारे शरीर में ब्लड प्रेशर को बढ़ा देती हैं। दूसरा सीरियस इशू है हियरिंग इम्पेयरमेंट। ये नॉइज पोल्यूशन के सबसे आम प्रभावों में से एक है। तेज साउंड्स के लगातार संपर्क में रहने से हम हमारी सुनने की क्षमता को खो सकते हैं। मानव शरीर पर साउंड के कुछ और भी प्रभाव हैं, जैसे कि चिंता, तनाव और मानसिक थकन। क्या हम नॉइज पोल्यूशन को कम कर सकते हैं? जी हाँ, बिल्कुल कर सकते हैं। यहाँ कुछ मेजर्स हैं जिनसे हम नॉइस पोल्यूशन को कंट्रोल कर सकते हैं। हमें सड़कों पर या आसपास के इलाकों में वाहनों के हॉर्न्स के इस्तेमाल को कम करना चाहिए। हमें केवल तभी हॉर्न बजाना चाहिए जब ये बहुत जरूरी हो। हमें सड़कों और बिल्डिंग्स के आसपास पेड़ लगाने चाहिए। लेकिन पेड़ क्यों? पेड़ साउंड पोल्यूशन कम करने में कैसे मदद करते हैं? ये नॉइस को एब्जॉर्ब करते हैं। हम नॉइस पोल्यूशन को कम करने के लिए और क्या कर सकते हैं? इंडस्ट्रीज रेजिडेंशियल इलाकों से दूर सेट की जानी चाहिए और वाइस वर्सा। पार्टीज, त्योहार जिनमें ज्यादा साउंड होता है वो भी रेजिडेंशियल इलाकों से दूर मनाए जाने चाहिए। हम आशा करते हैं कि नॉइस पोल्यूशन को कम करने में हम अपनी भूमिका निभाएंगे। अगले वीडियो में हम डिस्कस करेंगे कि हम साउंड्स को कैसे सुन सकते हैं और कैसे बना सकते हैं। आपसे अगले वीडियो में मिलते हैं।
Hello everybody. Today we are going to discuss a topic called Sound has Energy. Let us perform some activities to verify sound is a form of energy. First activity. Materials required: scissors, balloons, 2 cell phones, sand and a glass beaker. Procedure: take a glass beaker and place it on a table. Now take a cell phone and put it in the glass beaker. Take a balloon and cut it. Stitch the balloon around the open end of the beaker. If needed, tie the balloon with a thread or a rubber band. Now the stretched balloon acts like a diaphragm. Place some sand on the stretched rubber balloon and ask your friend to give a ring to the phone inside the beaker. Observe what is happening. We observe two things. If there is no sound produced inside the beaker, sand particles remain stationary. Dancing of sand particles takes place when phone was ringing. Conclusion: sound has energy to vibrate balloon diaphragm so that the dancing of sand particles takes place. Let us do another activity. Take a paper cup which is filled with water. Put it on a table. Take a drum and hold it besides the paper cup. Now start beating the drum. Observe what is happening. We observe two things like in the previous activity. If there was no sound produced from the drum, we don't get any ripples in the water. When we beat the drum, we will get ripples in the water. Conclusion: sound has energy to produce ripples in the water.
Now, we are going to perform an activity for observing the production of sound. Click each tab to know more. Take a rubber pad and place it on the table. Take a tuning fork and strike one of its prongs hardly on a rubber pad. Bring it near your ear. Now, trace your finger along one of the prongs of the vibrating tuning forks. Observe the changes in both cases. We have observed that a vibrating tuning fork produces sound. Here, when we trace a finger along one of the prongs of the vibrating tuning fork, we sense that the vibration is stronger towards the end. Take a beaker. Fill it with water up to the brim. Now take tuning fork and strike one of its prongs hardly on a rubber pad. Gently touch the water surface with one of the prongs of the vibrating tuning fork. Now, again take the tuning fork and strike one of its prongs hardly on a rubber pad. Then dip both the prongs of the vibrating tuning fork in water. Observe what happens in both the cases. We have observed the formation of waves on the water surface. We also observe that the water sprays out and makes a splashing sound. One of the prongs of the vibrating tuning fork touches the surface of water in the beaker with the side of the prong. If we touch the water with both the prongs of the vibrating tuning fork, we observe the water splashes on the sides and is sprayed higher than before. We learned that the vibrating objects produce sound. Vibration means to and fro kind of motion of an object. So, we conclude that all vibrating bodies produce sound. Sound cannot be produced if the body is not vibrating. Here, let us perform an activity to verify that the sound is a form of energy. Click each tab to know more. Take a glass and place it on the table. Now take a mobile phone and place it in the glass. Take a balloon and stretch it around the open end of the glass. Now take a rubber band and wrap it around the balloon. Make sure that the stretched balloon should act like a diaphragm by covering the mouth of the glass. Place some sugar crystals on the stretched balloon. Ask your friend to give a ring to the cell phone which is in the bottle. Now observe the movement of sugar crystals. We observe the dancing sugar crystals as phone produces sound inside the bottle. Here the vibration of diaphragm can be observed from dancing of sugar crystals. Suppose if there is no sound produced inside the bottle, sugar crystals on diaphragm remain stationary. We learn that when we produce sound inside the bottle, the stretched rubber sheet vibrates and makes the sugar crystals jump or dance. Hence we can conclude that the sound has energy to move sugar crystals, make them vibrate on the diaphragm. Similar to the stretched rubber sheet in the above activity, sound produced at a distance travels through air and reaches our ears and creates a sensation of hearing in our ears. Now, let us study about the propagation of sound to understand the pattern of sound wave. We know that sound is a form of energy. It travels through the air and reaches our ears to give the sensation of sound. We know that the matter or the substance through which sound is transmitted is called medium. When an object vibrates, these vibrations set the particles of the medium, that is air medium, around the object into vibrations. These vibrating particles do not travel all the way from the vibrating object to the ear. A particle of the medium in contact with the vibrating object is first displaced from its equilibrium position. It then exerts a force on the adjacent particle and gets displaced from its position of rest. After displacing the adjacent particle, the first particle comes back to its original position. This process continues in the medium till the sound reaches our ear. So, it is the disturbance created by the source of sound in the medium that travels through the medium and not particles of the medium. For this reason, sound waves are characterized by the motion of particles in the medium and are called mechanical waves. Note: pressure is related to the number of particles of a medium in a given volume. More density of the particles in the medium gives more pressure and vice versa. When a vibrating object moves forward, it pushes and compresses the air in front of it, creating a region of high pressure. This region is called a compression, represented by C, which starts to move away from the vibrating object. When the vibrating object moves backwards, it creates a region of low pressure called rarefaction, that is represented by R. As the object moves back and forth rapidly, a series of compressions and rarefactions are created in the air. These two types of pulses travel one behind the other, carrying the disturbance with it. This is how sound travels in air. Welcome to the chapter Sound. Now, let us know about the characteristics of a musical sound. In lower classes, we have studied that a sound of single frequency is called tone, while the sound which is produced due to a mixture of several frequencies is called note and is pleasant to listen. The sounds which produce pleasing effect on the ear are called musical sounds, while the sounds which produce an unpleasant effect are called noises. In an orchestra, a violin and a guitar may both be played at the same time. Both sounds travel through the same medium, that is air, and arrive at our ear at the same time. Both sounds travel at the same speed irrespective of the source. But the sounds we receive are different. This is due to the different characteristics associated with this sound. There are three characteristics by which we can distinguish a musical note from other. They are pitch, loudness, and quality. Click each tab to know more. Pitch. Pitch is a term used to describe how high or low a note being played by a musical instrument is. It is the characteristic sound of a musical sound by which we can distinguish a shrill sound from a growling sound, even though the two sounds may be of the same intensity. Actually, pitch of sound is the sensation conveyed to our brain by the sound waves falling on our ears, which depends directly on the frequency of the incident sound waves. Frequency is measured in Hz, with one vibration per second being equal to 1 Hz. A high frequency produces a high-pitched note and a low frequency produces a low-pitched note. In musical terms, the pitch of the note determines the position of the note on the musical scale, which is denoted as shown on screen. Note: the tuning fork set is prepared based on the above frequencies. Loudness. If we hit a plate with a stick lightly, we hear a soft sound. If we hit the same plate hard, we hear a loud sound. The reason for this change in intensity of sound is due to another characteristic of sound, the force with which an object is made to vibrate. Loud sound can vibration of the source, the greater is the intensity, and hence loudness of sound and vice versa. Loudness also depends on the distance between the listener and the source of the sound object. Quality. The quality of timbre of sound is that characteristic which enables us to distinguish produced by a tuning fork, a violin, and a piano playing the same note. Fundamental frequency equal to 440 Hz, with equal loudness is as shown on screen. Now, we are going to do an activity for observing the changes in sound. Click each tab to know more. Take 5 metal glasses and place them on a table. Pour different quantities of water into 5 metal glasses. Now, take a wooden stick and strike the metal glasses gently with a wooden stick. Observe the changes in sound. We have observed that each of the glasses will have a different tone when we strike them with the wooden stick. Here, the glass with the more water, less air gap will have the lowest tone, while the glass with the less water, more air gap will have the greater tone. We learned that the small vibrations are made when we strike the glass. This creates sound waves which travel through the water. So, glasses filled with water up to a different height produces a different sound based on the amount of air gap present in the glass. Thus, we can conclude that the sounds are produced by the vibrating bodies and by the air passing through orifices of the instruments like musical instruments. Jal Tarang works based on the principle of change in quality of sound. The Jal Tarang, one of the most rarely heard instruments today, is among the oldest instruments in the world. It consists of metal bowls filled with water and stuck by 2 wooden sticks.